We are now discussing about probabilistic algorithms. In the last two lectures, we have seen probabilistic algorithms for numerical integration and counting. The agenda for this lecture is to discuss probabilistic algorithms for verifying matrix multiplication. Given three square matrices A, B and C, the problem is to verify whether C is the product of A and B. So, it is not to find the product, but to verify whether a given square matrix is the product of other two matrices or not. So, that is the agenda for this lecture. Probabilistic algorithm for verifying matrix multiplication, and we are going to see a Monte Carlo algorithm for that. And what are they? They are probabilistic algorithms with small non-zero error probabilities. They allow to have incorrect results, but with very small probabilities, and they are useful when there is no correct or tractable algorithm not for solving a given problem. If there is no algorithm or no efficient algorithm, then it is useful to have an efficient Monte Carlo algorithm which is allowed to give wrong result but with very low probability. Suppose P is the probability that a Monte Carlo algorithm A giving correct answer to an arbitrary instance of a problem, then the algorithm is said to be P correct. P is the probability of correctness. And for Monte Carlo algorithms, P may not be 1 always. The probability of correctness P of a Monte Carlo algorithm may depend on the size of the instance, but should not depend on a particular instance. For example, if you are looking at, say, the sorting problem, the correctness may depend on the number of elements in the input set, but given an input set of size n, it should not depend on different inputs of size n. That is what I am trying to tell. It can depend on the size of the input, but on a fixed size, it should not depend on various inputs of the same size. That is a property. Monte Carlo algorithms have the property that a small increase allowed in the execution time can lead to a significant reduction in the error probability. If P is the correctness probability, 1 minus P is the error probability, and this is a non-property of any Monte Carlo algorithm, or in a notion, that is how a probabilistic algorithm is classified as Monte Carlo. A small increase allowed in the execution time can help you reduce the error probability to a greater extent. So, these are some properties and facts about Monte Carlo algorithms. Now, consider our problem. It is verifying matrix multiplication, not performing matrix multiplication, but just verifying the correctness of a given matrix multiplication. This is the problem. Given three square matrices A, B and C, each of order n by n, check whether C is the product of A and B. Example, here three square matrices of order 3 are given, A, B and C. You want to check whether C is the product of A and B. How will you check whether C is the product of A and B? In a deterministic process, what you can do is, you first obtain the product of A and B. So, in this example, this is the product that you want to get first. And after that, you check whether the product minus C is the 0 matrix. If it is 0, then this equation is correct, because AB minus C is equal to 0. For the given instance, it is not 0 matrix. In these two positions, you have non-zero values. So, AB is not same as C. C is not the product of A and B. See, what we did is, we want to verify whether C is the product of A and B, and in this method what we did is, we obtained the product and then we check whether the given matrix is the product or not. So, what is the complexity of this verification procedure? I mean the time complexity. For the naive matrix multiplication algorithm, it is theta of n cube, 3 nested loops, that is the straightforward approach for matrix multiplication. So, for doing this, you need order of n cube, and for subtraction, order of n square. So, in total, order of n cube. And another efficient matrix multiplication algorithm is proposed by Walker-Tresson, and whose complexity is theta of n to the power 2.81 using divide and conquer. And the asymptotically fastest known algorithm takes order of n to the power 2.37 time. So, that is the best known matrix multiplication algorithm. So, if you follow this approach, which is deterministic for verifying matrix multiplication, then this is the best known complexity, in general order of n cube. But we can have a probabilistic algorithm. We shall see a Monte Carlo algorithm in this lecture, whose complexity is upper bounded by n square, order of n square. So, that is useful because we are getting a more efficient way of verifying matrix multiplication. What we want to do is, we want to check whether the product of AB minus C is 0 matrix or not. Let D be the LHS. We do not know what D is. Initially, we have not computed D. D is a square matrix, that is what we know. And suppose capital S is a subset of rows in this required matrix. For example, maybe a subset of 2 rows. Now, you consider the sum of these rows. In this case, 0 plus 0, 0, 1 plus 0, 1, 0 plus 1, 1. This is the sum of the rows, and which is non-zero. That means there are some non-zero elements in the subset of rows. So, you can conclude in this case that this equation is not correct. If the LHS matrix is a 0 matrix, then the sum must be 0. And if the sum is non-zero, the sum is 0. If the sum is non-zero, you can conclude that C is not the product. But suppose the sum is 0, say you are selecting 2 rows, finding the sum, observing it as 0 at every position in the row matrix, then can you conclude that C is the product of A and B? No, you cannot. Why? Because there may be a non-zero row like this, which we are not including in the subset. So in the second case, we are not sure about whether C is the product of A and B, but in the other case, we are sure about it. We got an evidence that C is not the product of A and B. Thus, we can decide whether C is the product of A and B by checking whether the sum of subsets of rows is a 0 vector for an arbitrary subset of the required matrix in the LHS. So, we want to check whether the LHS matrix is the 0 matrix. For that, we just found a way of doing it. What is it? You find a subset of rows of that matrix and find the sum. You are getting a row matrix or a row vector. You see whether that is 0 or not. And if that is non-zero, we are sure that C is not the product of A and B. If it is 0, we don't know whether C is the product or not. Now the question is, what is the efficient way of getting the sum of the subset of rows in that matrix? So I can tell you an idea, which is what is explained in the textbook. Let X be a binary row vector of length 3, which is the dimension of each of these matrices, and D be a 3 by 3 matrix, any 3 by 3 matrix. For example, X is a row vector of length 3 and D is a 3 by 3 matrix. Then what is the dot product of X and D? If you multiply X with the D, it is a 1 by 3 matrix. This is a 3 by 1 matrix. You will get a 1 by 3 and 3 by 3. You will get a 1 by 3. So you will get the result as row vector of length 3 itself. For this example, you can easily verify that this is the product vector. And it is not difficult to see that X into D is actually the sum of rows of this matrix, and you are taking the ith row in the subset if Xi is 1. Here XD is row 1 plus row 3, that is XD. That you can easily verify from the equation for matrix multiplication. So wherever you put a 1 in the row vector, you are including that row, and if you put a 0, you are not including it. See that it is a binary row vector. So that is a way of getting a subset. Thus, to obtain the sum of an arbitrary subset of the matrix D, what we can do is, we can find X into D, where X is an arbitrary or a random row vector of size n. I hope you are getting me. So what we want to do is, we want to verify whether C is the product of A and B. For that, we want to verify the correctness of this equation, and for that what we did is, we want to multiply D, which is this matrix, with a binary random row vector. That is what we found in this case. This is D. What is D? D is nothing but the LHS of this equation. If you multiply that D like this. If you take a random row vector which is binary, and if you multiply that with the matrix D, what you are getting is the sum of a subset of rows. And if you have formed this binary row vector uniformly at random, you are finding the sum of rows where the rows are selected uniformly at random. So now this is the equation that you have, right, in the LHS. What is it? If you multiply inside, you will get x into a. I am taking x into a, then this is the equation, right? It is equal to 0 means I can say that xab is equal to c, and then I am multiplying inside. This is the equation I am getting. I hope you are following me, otherwise please see that it's correct, because what I am doing is in this equation I am multiplying x inside, it is xab minus xc. Then after that I am taking that minus xc to the other side, so I am getting this equation. Now this requires 1, 2, 3, 3 matrix multiplications, but we can see that even though it requires 3 matrix multiplication, it is more efficient than the naive deterministic procedure that we discussed. See that what is the complexity of performing x into a? X is a row vector binary, so you can easily see that it is a theta of n square operation, a row vector, and this is an n by n matrix. And what is the result? Result of doing it is again a row vector. You call it as y. So you called it as y, this is y, then y multiplying with b. This is again a theta of n square operation, because a row vector of size n to be multiplied with an n by n square matrix. So it's again an order of n square operation. And this is again order of n square now, because a row vector of size n multiplied by an n by n square matrix. So each of the multiplication is order of n square, and hence we are getting an order of n square procedure. So this is what we are trying to do. Given 3 matrices and their order, what we do is we are forming a random binary row vector. I hope you remember this basic probabilistic procedure which returns either 0 or 1. Okay, you take the seal of that, then you will get, or floor of that, you will get this binary value. And after that you check this equation whether it is correct or not. If they are same, then you return true, otherwise you return false. So this is the algorithm that we have. And now note that if this is the case, if the LHS, that is a into b minus c, is same as the minus c is 0, then we know that the answer may not be correct. But if they are not same, that is the else part, the answer is correct. You are getting an evidence that C is not the product of A and B. So the else clause is always correct, but we don't know about the true or then clause, because there may be a row which we are not including in the subset containing a non-zero value. So the then clause may or may not be correct, but the else clause is always correct. Look at an example. This is the same example, and if we get the random binary vector as 1 1 0, we can easily see that the LHS is this row vector and the RHS is this row vector, and they are matching. So you are returning true, and you already know that C is not the product of A and B. but this algorithm is returning an incorrect answer. But suppose you get this random vector or the values as this for the random vector 0, 1, 1. In this case, you can see that the second and the third components are mismatching, and in this case you got the correct answer, false. And because you got false for one vector, it is true that C is not the product of A and B. And now you can see that the probability of correctness is 1/2 because it returns either true or false. If it returns false, the algorithm is correct. True, we don't know. Okay, there are two possibilities as outcome, true or false. False is always correct. We don't know about true. So you can say that it is half correct. The probability of correctness is half. And thus we have a half correct Monte Carlo algorithm for verifying matrix multiplication. This is what we have. It is only half correct. Then the question is, why should you go for a procedure like that? It is an order of n square procedure. For getting a half correct algorithm, you don't have to do anything. What you do is, you just flip a fair coin, and if you get heads, you return true, otherwise you return false. Even if you do that, this is an order of 1 algorithm. You are getting a half correct algorithm, probabilistic algorithm, right? So what we discussed is not an interesting procedure because you don't have to do all those things. You just flip a coin. If it turns heads, you return as true, otherwise false. Okay, this is a half correct algorithm. If our algorithm returns false as output, then we can conclude that that is not this algorithm, the algorithm that we discussed in the previous slide. If that algorithm returns false, then we know that for sure C cannot be the product of A and B. And if our algorithm returns true, the previous algorithm, then we are not sure about whether C is the product of A and B. So in the later case, we can run the same algorithm again to reduce the error probability, and that is why you are getting a Monte Carlo algorithm. So you run the algorithm once. If it returns false, you can stop because it is then correct that C is not the product of A and B. But suppose the algorithm in the first execution says true, we don't know whether AB is same as C or not. Then what you do is you execute the algorithm again. So this is what I am trying to tell. You repeatedly execute that algorithm. From 1 to k, you call the previous algorithm, and if that algorithm returns false, you are sure that C is not equal to A, product of A and B, then you return false, otherwise you return true. So now you are getting a new probabilistic algorithm. And what is the error probability of this algorithm? If this algorithm returns false, then it is correct. Then when it is not correct, when the algorithm returns true and the matrix C is not the product of A and B. When it happens when the matrix C is not the product of A and B, but every time, for all the k times you execute, this returns true. And not that this returning true is probability 1/2, and for this sequence the probability is 1/2 to the power k, and it can be written as 2 to the power minus k. So 2 to the power minus k is the error probability. So what is the correctness probability? 1 minus this is the correctness probability. So we are getting a 1 minus 2 to the power minus k correct Monte Carlo algorithm. Now if you substitute the value of k as 10, that is if you execute this algorithm 10 rounds, you are getting an algorithm which is more than 99.9% correct, or the correctness probability is 0.99, almost 1. You are getting an almost correct, almost precise algorithm if you execute this 10 number of times. So that's good. So this is a Monte Carlo algorithm. Only 10 times you are executing. Now we can have a control on how many times you want to execute the algorithm. If you want to control that, you want to get an epsilon correct algorithm, right? Error probability is, sorry, epsilon, not epsilon correct, 1 minus epsilon correct. If you want to control the error probability to epsilon, what you can do is you take k as log 1 by epsilon to the base 2. This is log 1 divided by epsilon to the base 2. Then you call this algorithm with k as this value. And what is the complexity? N square is the complexity of this algorithm, and you are executing that for k times. So what is k? K is log 1 by epsilon to the base 2. So the complexity is n square multiplied by log 1 by epsilon. And what is the error probability? You know what is the error probability is. It is 1 over 2 to the power k. And what is k? You substitute the value of k. It is log 1 by epsilon to the base 2. So what is 2 to the power log n for some n? It is n itself. Okay, it's a non-fact. So you are getting 1 divided by epsilon is nothing but epsilon. So this is the way you can control the error probability. Whatever be the permissible error probability, you pass that as an argument. Then what you do? You take k as log 1 divided by that error probability in the base 2. And if you call this algorithm with k as that value, you are getting a probabilistic algorithm whose error probability is the given value epsilon. With this, we are finishing this lecture. Today, we looked at probabilistic algorithms for verifying the correctness of a matrix multiplication. The naive deterministic algorithm takes order of n cube time, but we got a probabilistic algorithm whose complexity is order of n square. And if you want to control the error probability to a given value, you are getting an order of n square multiplied by log 1 by epsilon, where epsilon is the error probability, which is very near to order of n square algorithm, and which enables you to control the error probability. Thank you.